Okay, we're back here. It's Thursday for our final set of notes on Chapter 21, dealing with heat engines and refrigerators. It's not only the final set of notes for the chapter, but the final set of notes for the first unit, which means unit exam, Monday the 22nd, covering chapters 15, 18, 19, and 21. On this last chapter, we're only covering sections 1 through 4 on the exam, so we will finish that up today. So where did we end up? Okay, well, we reviewed heat, work, and energy. Should go back and do that. We analyzed PV diagrams of heat engine cycles just to illustrate the methodology, and we did this example here of a heat engine. And so what we did is for each of the three processes, process A, B, and C, which comprise the cycle, we applied the first law of thermodynamics along with the type of process. For example, A is an adiabatic process. So we applied that to determine the sign of the heat added, the sign of the work done by the system, and the sign of the change in the internal energy. So you should be able to, for any type of closed system, you should be able to make a table similar to this, and you should be able to provide your reasoning, as we did above here, using the first law to justify why we chose the signs that we did. And then finally, at the end of each stage, you should be able to say what is actually being done and how it contributed to the goal of the cycle here, so for this heat engine. So you're going to be doing this for the Otto cycle, which is a more realistic heat engine that we're going to cover in class. You should be able to make the table for this and analyze the PV diagram. Should also be able to do it for a refrigerator. So we're going to cover both of these as far as, the YouTube video and a superficial treatment, and then I am leaving it to you, homework problem 8, to make this table and to justify your reasoning. And there's a homework problem on homework 4 that will also give you some more practice, but you should be able to do this for an exam. You really need to understand what an adiabatic process, what an isothermal process is, in this case a constant volume process, isochoric. You have to have these mastered as to what the process is, what the amount of work done is in that cycle, and apply the first law of thermodynamics to that cycle to make a table something like this. So we covered this. Where are we going today? We are going to start off with a practical example of a heat engine, the Otto cycle, which is a pretty good approximation to your car engine. And then we're going to discuss the refrigeration cycle, which is a heat engine in reverse. We're going to start both of them with a short YouTube video. I found a couple really instructive YouTube videos that were short. Then we're going to look at the PV diagram for each and describe those. So let's get started here.
There's a certain strain of bacteria called Lactobacillus reuteri that will help you grow bigger balls.
This is not what we're watching. Okay.
My class and I had a go at making short stop-motion animations to show how the internal combustion engine works. This rather nice engine is from a Ferrari Testarossa. The white particles on the left-hand side here represent the mixture of particles of air and fuel. The inlet valve opens as the piston moves down. As the volume of the cylinder increases, this draws air and fuel mixture into the chamber at constant atmospheric pressure. The piston then continues to move upwards, either forced upwards by the momentum of the crank or the force generated by the other cylinders in the engine. This compresses the fuel and the air mixture in a roughly adiabatic compression. In a petrol engine, the spark plug at the top of the cylinder ignites the fuel at this point here. This is at the point of maximum compression. This ignition causes a rapid increase in pressure. After combustion, I've changed the particles in the animation from white to blue to represent the combustion products. The combustion products are now at a very hot temperature and pressure, and a very high pressure, and they force the piston back down the cylinder. This is called the power stroke. In the final phase of the cycle, the exhaust valve opens. As the exhaust products are at a pressure much higher than atmospheric pressure, they tend to rush out of the open exhaust port. Finally, the momentum of the piston continues to push it back to the starting position, ready for the next inlet stroke. Some people like to remember the 4 stages of the engine cycle with these 4 words: suck, squeeze, bang, and blow. Let's have a look at some animations that my students created during their recent physics lesson. Although this first animation is rather simplistic and doesn't include much detail of the cylinder and valves, I rather like it for its scientific accuracy. The students have represented fuel and air particles with blue and white dots, and they change to orange to indicate combustion has taken place. This second animation is rather neat and nicely drawn. The students have used an orange colour to indicate the high pressure in the cylinder, and they have changed the colour of the combustion products to black. One slight problem with this animation is that the number of particles in the cylinder doesn't seem to stay constant even when the valves are shut. This animation has been excellently drawn and also cleverly engineered using some split pins to show the rotation of the crank. This nicely illustrates how the momentum of the crank carries the piston upwards during the compression and exhaust strokes. I like how this final animation uses paper confetti from a hole punch to represent the different particles: white particles for air, yellow for fuel, and orange for the combustion products. The orange combustion products cleverly spread out from the point of the spark plug. The other students in the group affectionately christened this animation the rubbish compressor. I'm now going to explain the stages of the engine cycle in a little more detail. This diagram on the right is a pressure-volume diagram. P here for the pressure of the gas on the y-axis, and V here for the volume of the cylinder on the x-axis. The cycle shown is the idealized cycle for a petrol engine or Otto cycle. The green dot makes its way around the cycle roughly in time with the cylinder. You might be able to spot the different stages of the cycle on the diagram. I'm now going to look at each of those stages in a little more detail. In the inlet or suck stroke, the volume of the cylinder increases as the valve is open to the atmosphere, drawing in air and fuel. Because the valve is open, the pressure remains at atmospheric pressure. In the compression stroke, the valves are closed. As the piston makes a tight fit with the cylinder, the gas is compressed. This curved line on the graph is an adiabatic compression, one in which no heat is exchanged with the surroundings. This means that the pressure and temperature of the gas both rise. The ignition happens very quickly in a petrol engine. In the idealized Otto cycle, the volume of the cylinder remains constant, while the pressure and temperature of the gas increase during combustion. In reality, of course, the line can't be completely vertical, as the piston never stops moving. The power stroke is represented in the Otto cycle by an adiabatic expansion, this second curved line here. During this expansion, the volume of the cylinder increases and the pressure and temperature of the gas decrease. This does work on the piston, pushing it down. The exhaust phase is represented by another vertical line on the Otto cycle. The pressure reduces at constant volume. When the exhaust valve opens, the gas is at high pressure and so it rushes out of the open valve. The final exhaust stroke pushes out any remaining gas at low pressure and brings the green dot back to the starting position. Hopefully you can identify all of those processes as the green dot makes its way around the Otto cycle. The area enclosed by the graph represents the amount of work done by the engine per cycle.
Okay, so that was a very good video. It's probably the best one that I have been able to locate regarding the Otto cycle. You should be able to, on an exam and in your exam preparation, you should be able to explain what's happening in each stage of this Otto cycle. In relation to what's happening, what is the sign of the heat added, the work done by the system, the change in the thermal energy. You should be able to make one of those tables, and you should be able to describe physically what's going on in each of those steps of the Otto cycle. So to do that, to understand it and to explain it, you have to understand the PV diagram, right? So process one, which is the intake stroke, where the gas in the cylinder expands, right? The piston moves away from the spark plug, the volume increases, and the gasoline comes in at constant pressure, the gas-air mixture, to fill the volume. This is an isobaric process, constant pressure, okay? Based on constant pressure, you should understand what's going on in terms of work, in terms of heat added, and in terms of change in thermal energy. Then the adiabatic compression, which is going from 2 to 3, you should be able to explain, based on the fact that it's adiabatic, what's going on in terms of the sign of the work done, the heat, which is obviously 0, and the change in the thermal energy. And for each of these other steps, you should be able to describe this process on the exam. And in fact, this is part of homework problem 8, is to go through and to make that chart and explain it based on. So I encourage you to go over the video again, to look over this PV diagram, and this is where you really need to understand these types of processes. Then the workout is just the area under the curve. Now this is a kind of complicated shape, and you can go through as one of the homework problems was, which you should thank me for not giving you, and you can derive, or you didn't, but you could have, that the efficiency of the Otto cycle, which is you calculating the work output divided by the heat input, is the efficiency is 1 over 1 to the R gamma minus 1. Now, R is what's called the engine's compression ratio. It's the ratio of the maximum volume when the piston opens up fully, divided by the minimum volume of the cylinder when the piston fully compresses the gas. So this ratio is called a compression ratio. And then gamma, remember we discussed this a little bit ago with adiabatic processes, is the ratio of the specific heat at constant pressure divided by the specific heat at constant volume. And air is a diatomic gas, so gamma 7 over 5, 1.4, and our formula for the efficiency of an Otto engine, then, interesting, it depends only on this compression ratio of the engine. So I made a little plot here. If you look at, I varied the compression ratio from 0 to 35, and I calculated the efficiency on the vertical axis. And you see that as the compression ratio, maximum volume to minimum, in other words, how well can you compress and expand this cylinder, the volume, as the compression ratio gets larger, the engine becomes more efficient, right? you can start off by pulling in more of a fuel-air mixture and by increasing the volume, and you compress it down more. You're increasing the temperature and the pressure to higher temperature, higher pressure, which helps it to burn more efficiently. So for a typical compression and for a typical gasoline engines, the compression ratios are around 8 to 12. So if you say that middle value is around 10, that means that the thermal efficiency, which is the ratio of the mechanical work done divided by the heat input, is about 60% at typical compression ratios. So kind of an interesting result that the efficiency of an Otto cycle depends only on the compression ratio of the engine. So the next stage that we're going to go into, we're going to cover refrigerators, and this is in section 21.4 of your text here. Here's a simple model of a refrigerator, and recall down here, here's our energy transfer diagram. We went over this in the last set of notes. Remember, the job of refrigerators is to move heat against the temperature gradient, right? So second law of thermodynamics says heat will flow naturally from hot to cold, but that it doesn't naturally or spontaneously flow from cold to hot. So we need to supply some work to extract heat from this cold reservoir and to push it against the temperature gradient toward a warm reservoir. And so for a refrigerator, the cold reservoir would be the inside of your refrigerator, and the warm reservoir would be your kitchen. So we have to supply work to pump heat against the gradient. And we'll discuss a simplified refrigeration system in the next chapter. And so we'll start off again with a YouTube video. And here's a basic PV diagram and approximation for the refrigeration process, which we'll study a little bit after we watch the video. You should be able to again make that table with the signs again and explain what is happening in each stage. So we saw before when we compared the heat engine and the refrigerator is that all the arrows for the refrigeration cycle are in the opposite direction from the heat engine, right? The heat engine, the arrows were all opposite of this. You had heat spontaneously flowing from hot to cold, and we got some work out of it, and so it was W out instead of W in, and the rest was exhausted into the cold reservoir. The refrigerator, the arrows are in the opposite direction, right? We're trying to move heat from the cold reservoir, so flip the arrow. We need some work in, so the arrow goes in, and we're kicking it out as exhaust to the hot reservoir. So all the arrows are in the opposite direction. So let's start by watching a YouTube video here of the refrigeration cycle, and then we're going to go into it in a little more detail on the PV diagram and describe it.
So just a standard air conditioning system. All right, so you have two items that separate the low pressure and the high pressure on this system. And the one is the compressor that's up high, and then the other is the metering device where in this picture you see it's down low. All right, so how the refrigeration cycle works is it takes low pressure, low temperature vapor refrigerant, it comes into the compressor, and out of the compressor it comes out as a high temperature, high pressure vapor refrigerant. In fact, it's at its hottest spot on the entire system right there. As it enters into the condenser coil, it starts rejecting heat. As it rejects heat, it starts turning into a saturated state in the middle of the condenser coil. All right, a saturated state is where vapor and liquid both exist at the same time. All right, so right there, right after the saturated state where it turns into a complete liquid until where it comes out right next to the service valve, the temperature decrease as it's rejecting heat. The temperature decrease in liquid form is called the subcooling. All right, the saturated state is where it's transferring most of its energy at. All right. The refrigerant is what is carrying the heat and moving it, rejecting it and absorbing it in the refrigerant itself. And most of that energy transfer occurs right in that saturated state. All right, so it comes from the saturated state in the middle of the condenser coil. It continues to reject heat as a complete liquid until it comes out of the condenser coil. Then it comes down in the picture here, and then it makes a left, and then it goes in through the filter dryer. The filter dryer is there to absorb any moisture in the system. All right, it has a fixed capacity, and that's it. All right, it comes through that, and then it hits the metering device. The metering device allows for a pressure change. All right, when you have a pressure change, so you have high temperature, high pressure liquid refrigerant coming into the metering device, and then it turns it into a low pressure, then what happens is it automatically makes it a low temperature as well. So if you decrease temperature, then pressure will decrease. If you decrease pressure, then temperature will decrease. So in this case, we have a high pressure, high temperature liquid refrigerant coming through and hitting the metering device. The metering device is only going to allow a small amount through, all right? And then it turns into a low pressure, low temperature, 80% liquid, 20% flash gas mix. But it's mainly going to be a low temperature, low pressure liquid, all right, until it gets to the middle of the evaporator coil. So the refrigerant is actually absorbing heat once it enters into the evaporator coil. As it absorbs enough heat, it turns into that saturated state in the middle of the evaporator coil, all right, where most of the energy absorption is taking place. And then right after that is where it turns into a low pressure, low temperature vapor. All right after the saturated state, it turns into that low pressure, low temperature vapor, all right, until where it comes out of the evaporator coil, it's still absorbing heat. As it comes out of the evaporator coil, right at that point right there, the temperature increased from the saturated state in vapor, right at the end of the saturated state in vapor, to where it comes out. That's called the superheat. If you continue along, you keep coming up as a low pressure, low temperature vapor. You come up and then you make a right, and then you come over to the service valve. All right, so that's where we take a superheat reading at. All right, so if you took right in the middle of the evaporator coil, right after the saturated state where it turns into a complete vapor, the temperature increased from there all the way over to the service valve next to the compressor. That's called the total superheat. All right, after that, it just enters back into the compressor as a low pressure, low temperature vapor refrigerant, and the refrigerant cycle starts all over again. All right, well, I hope you enjoyed yourself.
Okay, so before we get into the phase changes, like the evaporator and the condenser and the critical role that they play, let's just try to understand the refrigerator that we saw in the video using the PV diagram. So you have a closed loop here, and you have the compressor, and then you have the condenser here, and then you have the expansion valve, which expands the gas here, and then you have the evaporator here. So let's look at each step in the process. So let's start here at point 1 here. And what we have right here is we have a gas that is at a cool temperature, right? It's a liquid, sorry, that's at a cool temperature here coming in from the evaporator. And in order for heat to be transferred from the refrigerator body, the inside of the refrigerator, to the coolant, the temperature of the refrigerant has to be lower than the temperature inside the refrigerator, because that's the only way that that's the direction heat's going to flow, right? So the whole job of this expander or this expansion valve is to lower the temperature of the fluid to a temperature lower than the temperature of the inside of the refrigerator, so that heat can be transferred from the inside of the refrigerator to the fluid. And so that's this process here going from 1 to 4 here, is you have an adiabatic expansion, okay? And by adiabatic, it means no heat is added or removed. And when a gas expands adiabatically, the volume increases and the gas cools. So that's what the purpose. The gas expands and cools. Okay. Now with the gas the liquid is at a temperature cooler than the inside of the refrigerator, so heat is going to be transferred to the fluid, and that is going to, by absorbing the heat, remember some of it's going to evaporate the liquid, a change of latent heat. So the volume of a given amount of mass will increase, and then we go to this point, okay? So we've added heat to it, the heat has gone into latent heat and it's increased the volume. Now we go through the compressor. Now the whole job of the compressor is to take this low temperature gas with a little liquid and to raise its temperature to a higher temperature than the surrounding high temperature reservoir, the kitchen. Okay, so that's the whole purpose here. You have an adiabatic compression of the gas. Remember, so if you compress a gas without adding heat, then the work done in compressing, the work done to compress the gas volume goes into increasing the temperature and the pressure. And the whole point is to increase, the compressor's whole job is to increase this temperature to a temperature that's larger than the temperature of the surrounding room, because that's the direction heat's going to flow. So the temperature of the fluid here has to be higher than the temperature of the surroundings in order to kick the heat out into the room. And so you have this adiabatic compression here. Remember, when gases are compressed adiabatically, they heat up. And so that's the whole job of the condenser. Okay, now we're going through this high temperature heat exchanger, which is the condenser, and the job of that is to condense, meaning it loses heat, and that will result in condensation from the gas phase to the liquid phase. The latent heat gets kicked out, and so when a gas condenses, its volume decreases, it becomes a liquid, and so this is what's called an isobaric process, constant pressure. Now we get to this point 2, and we've exhausted the heat, but this coolant this refrigerant is still at a much higher temperature than the inside of the refrigerator, so we need to cool it. Okay, so we can cool it by expanding it. And so this adiabatic expansion, remember, when Q is equal to 0 and a gas expands, the work done by the gas cools the gas. And so the gas expands enough so its temperature this liquid expands enough, that its temperature is larger or is lower than the temperature here of the inside of the refrigerator. And so we can transfer heat again from the inside of the refrigerator to the coolant. And so you have to have a coolant temperature at this point here that's lower than the inside of the refrigerator to transfer heat to the coolant. And up here you have to have a temperature of the coolant higher than the surrounding room in order to kick the heat out into the room. So you should be able to take this model PV diagram for the refrigeration cycle, and you should be able to make the table of signs, the plus, minuses, and 0, just like you did before. Explain what type of process each of these. You have 2 adiabatics and 2 isobarics, and what is going on with each process. Now, latent heat plays a very important role in the transfer of heat. And remember, back from chapter 18, I think, where we discussed latent heat, 19, and remember that it takes much more energy to change the phase of a substance than it does to change its temperature. And so, for example, in this evaporation stage here, this can absorb a lot of heat from the low temperature reservoir. It can absorb a lot of heat and carry it away as latent heat of evaporation. Then it gets compressed, and when it condenses, all of that latent heat that was put in down here, when the gas condenses, that gives it off as heat, the energy off as heat, and that gets extracted to the room. And so that's why latent heat in evaporating and condensing the gas is used, because it has the ability to transfer large amounts of heat. And so the sole job of the evaporator system, remember, is to transfer this energy mainly through latent heat from the cold reservoir to the coolant. The main job of the compressor is to subsequently raise the temperature of this vapor to a higher temperature than the surrounding room, so that heat will get transferred out. That's the job of the compressor. The job of the condenser is to condense this vapor back into a liquid, extracting this latent heat out. And then this, what's called the throttling or the expansion valve, that's job is to expand the fluid, and again to lower its temperature to a temperature lower than the inside of the refrigerator, so that heat will be transferred into the fluid. Now, fortunately, there's the working fluid, which, for example, Freon, has a low boiling point, okay? And so this is operated very close to the boiling point at low temperatures. And so that will facilitate a lot of that latent heat transfer. And then here's just another picture of the refrigerator, which pretty much repeats what was in the video. So you should be able to understand the steps of the process for a refrigerator, just like an Otto cycle for a heat engine. And you should be able to look at the PV diagram, explain each step, and make your table with the signs. There's another homework problem that will give you practice for that. So this pretty much concludes Chapter 21, and it concludes Unit 2. So I encourage you to begin working on Homework 4, to look at these notes again and really understand these processes for refrigeration and for the Otto cycle. Okay, we didn't cover that many engines and refrigeration types, but you should be able to understand the process for each of these. And you should be able to go back to these unit learning objectives, and you should be able to do each of these on an exam. If not, come into office hours next week, a whole week before the exam to prepare. So that pretty much concludes the lecture. Have a great weekend. Bye.